Okay, we only have 2 lectures left, so I want to talk today, the last 2 lectures, just kind of, Lindsay, would you mind turning off one of the front lights? Yeah, perfect, thank you. Talk to you we're just in the next 2 lectures, we're just going to talk about different examples and applications in kinetics. We just don't have a lot of time to really systematically build up complex kinetic theory. So instead, I want to talk to you about a selection of topics to the next 2 lectures that are applications, very common applications of kinetic principles, okay? And so I have 2 very common types of kinetic events, if you will, kinetic types of experiments that are done in chemistry, in particular in organic chemistry. Again, these can be done with any sorts of chemicals, but often we see these things in organic chemistry. And these are really common kind of concepts and techniques that chemists use to study kinetics. And the one I want to first talk to you about is actually very relevant to the homework. Very, very relevant, kind of the guiding principle to the homework. So the concept that I'm going to be talking to you about today has a couple different names. 2 different topics today, but the first one is what's called the Curtin-Hammett principle. Right, named after Curtin and Hammett. Right, I don't know, some random white guys. Don't know who they are, but they are famous for one thing, and that's their principle. And the Curtin-Hammett principle again is going to be a mechanism, some sort of this kind of common reaction that can occur in chemistry. And the Curtin-Hammett principle tells us about the potential results of that experiment. Okay, you have some reaction that can maybe have what basically we'll see has multiple choices. You have a starting material that can maybe form 2 different products, right, through 2 different paths. And the question is, which one is preferred? Okay, so let's think about that. So let's think about having the idea here is the idea is a reaction of some starting materials, some reagents that has multiple pathways in competition, multiple reaction pathways in competition. Okay, so the idea is that you have a starting material that can jiggle around a little bit. If it jiggles one way, it goes through one step, one process to form a product, right? But you might be able to jiggle it another way and it goes and forms a different product. And so if you start with that material, given your conditions, what's the result? Do you will it prefer this result A or result B? Which pathway does it prefer? Or are they in competition, and how does that competition work? Right, so the idea is very simple. Let's imagine that we have a material A, our starting material A, and it could be multiple molecules, just some group of reactants A, that reacts with some rate, we'll say Ka, to form some product P1. Okay, we have a reaction that this can happen. Right. Just a normal old reaction, nothing fancy. Right, and imagine now that the A can also equilibrate with another species, we'll call B. Right, so let's assume that this is true. And that A is in equilibrium with some molecule B, right? Maybe these are isomers of each other. They could be, they could be anything. It really doesn't matter. It could be a negatively charged system and a neutral, right? Maybe you have an acid-base equilibrium here. But the idea is that if B exists in the solution, then it has the opportunity to react through a different rate to form some other product, P2. So we have a starting material that rapidly, maybe, we don't know if it rapidly equilibrates or not, but it can equilibrate to some other starting material B, and B forms a different product than A. All right, so what would the reaction coordinate for this look like? do it relative to delta G. Right, so let's just put A. Typically, when we do these situations, we put the starting materials. If there's a choice to go from A to B, then B goes to P2 or A goes to P1, we'll put A and B in the middle. Like we'll start from the middle and work out in our coordinate. So let's say, for instance, A is here. All right, and B could be above, higher in energy, the same energy, or lower in energy than A. So maybe we'll just for giggles, just to put B here. Right? And there may be some barrier that allows you to convert from A to B, right? And the rate of which conversion along this direction from A to B is K1 and K minus 1 to go reverse. Okay. And then each of these starting materials have their own paths that lead to the products. Right? So we can imagine, for instance, that A has this large barrier here that forms P1. I'll do that in a different color for you. Right? P1 is here. And then maybe B forms a different product of some energy, P2. Okay. And of course, these have rates KB and KA to convert from B to P2. So simple idea. If you guys have looked at the problem set carefully, looked at the figure 2 in the problem set, you may recall that the reaction coordinate in the problem set right now looks a lot like this. Right? The only difference now in the problem set 2, or sorry, problem set 6, is that there is an intermediate between A and B, right? That you have the R and the S, and then there's this A chiral enolate in the middle, right? So there's this extra step of the equilibration. But it's the same idea, right? You have two paths that are in competition with two starting materials that can equilibrate between each other. Right, and so the question I want to ask, of course, right, the big question we want to know, the big question is, what is, after the reaction occurs, what is the product ratio? That's a fair question. Right? This is exactly the question I'm asking in problem set 6. Of course, the math is going to be a little different because of that extra step in the middle, but the principle is precisely the same. Okay, so let's think a little bit about how to calculate this. All right, well, let's start thinking about the rates of formation. So we can write dP1 dt, which is equal to Ka times the concentration of A, and dP2 dt, which is equal to Kb times B. Okay. And of course, there's some equilibration between A and B. All right, so let's write a few, let's notate a few things. All right. So the first thing I want to notate on my diagram is the activation energies. So the activation energy for A, we'll call delta G double dagger A. And the activation energy for B is delta GB double dagger. Okay, so those are some numbers that we need. And we may want to also know the equilibrium constant between A and B. And so there is this delta G between A and B as well. We'll call that GAB. Right, and there's some equilibrium constant, right, associated with that energy difference. Of course, the way that I've drawn it here is that B is lower energy than A, right? So that means that this system prefers to be B. So if these are equilibrating together, we'll have more B than we have A by default. But if they're the same energy, of course, then they would have 50-50. All right, so what we want to do is we want to take this information we have here, and we want to calculate the ratio of P2 and P1. So we just need to do a little bit of math. So we could maybe say, right, if we think about it, what if we take the ratio of the rates? So what if we take this number and divide it by P1 dt? Like so. We would get something that looks like KB over B divided by KA over A. And let's think a little bit about what this derivative that we're taking. We're taking a derivative of a ratio of derivatives. So we can kind of think, well, if these are both moving along the same time trajectory, right? dt is tracking the same steps. Then this is per step. We could say, right, we could just roughly cancel out the dt's here. And we say that the change in P2 divided by the change in P1 is just equal to this ratio. Right? It's not too hard to then say, okay, well, if I think about how much does P1 and P2 change from t equals 0 to t equals infinity, then this is just the total change across the reaction of P2 and P1, right? So I could just write, I can basically just get rid of that when I integrate this out over all time, I get that the ratio of the products is equal to the ratio of the rates. But I can make one more simplification here, right? The ratio of the products has some rate constants in it, but it also has a ratio of B and A, right? But we know this value because B and A are in rapid equilibrium with each other. B and A are constantly going back and forth, back and forth, back and forth, back and forth, back and forth. So the ratio of B and A is fixed. Right? So let me just write that here, right? So the assumption that we're going to make here again is that K1 or K minus 1, which is again the rate that converts A and B, are much faster than KA or KB. So the idea is that A and B are constantly moving back and forth, right? They're constantly exchanging, and occasionally one of them will react to form the products. Okay, so A and B are exchanging rapidly. And what assumption can we then apply to A and B? Well, we can say that the total concentration of A and B, so the time derivative of the total concentration of the materials, is equal to 0. Right? Because if I lose a little bit of A, right? If A goes over to P1, I lose a little bit of A. But what happens is Le Chatelier's principle kicks in, and I replenish A with a little bit of B. Right? And then what? Actually, I should probably say this is the ratio. Excuse me. So let me change that. This is the ratio of the rates. Ratio of the rates, right? Because if I lose a little bit of A to go over to P1, then B will replenish A because of equilibrium, right? The concentration ratio of B and A are fixed to the equilibrium constant. So that means that this ratio between B and A is the same value regardless of conditions. Okay, so this means that again, B and A, the ratio of the concentrations of the starting materials is fixed. And it's fixed to the equilibrium constant for that reaction. Right? It's always fixed to this ratio set by the equilibrium constant. Okay, so I can use that fact that my ratio of B and A are always this value, KEQ. Well, I can substitute KEQ in here. Right, so what happens now is that the product ratio has no concentration dependence. my product ratio of my products, P1 and P2, has nothing to do with whether I have more B or more A. In fact, it doesn't matter at all. What only matters is the relative energy difference, the relative rates of the reactions, and the relative energy difference between the reactants. Right, so it's only about relative values. Right, this is the relative rates. And these are the relative abundances or concentrations. Okay? So here we have a kinetic property, which is the product ratio, and it's got nothing to do with concentrations. It's completely zeroth order. It only depends on thermodynamic properties. It depends on the thermodynamics between A and B, and the barriers, that's the speeds or the rates of the resulting product reactions. Okay. Let's see what the consequences of that is. All right, so what we have so far is that the product ratio we see is equal to some rate relationship times an equilibrium constant. Now, there is a good reason why I wrote down earlier these energy differences. I have energy differences between A and B, and then also have the activation barriers for each reaction. Right, so I can write my product ratio in terms of these barrier heights. Right? We can use the Arrhenius equation, which says that the rate of a reaction is some number A times an exponential of the activation energy divided by RT. And that KEQ is E to the minus delta G AB, the ratio between the energy ratio between the materials RT. Okay, so all we have to do is plug this stuff in. So we have A E to the minus delta G A over RT divided by A minus delta GB over RT times E to the minus delta G AB over RT. Okay. Now here's the brutal part, right? These are three energies that we don't really easily know. We can measure them experimentally, no problem. But maybe we can do a couple of simplifications here. We don't know these A's yet, but let's make an approximation, right? These are, let's assume again, this is liquid phase, condensed phase, right? The idea is, right, the assumption here is that A to P1 and B to P2 have identical or roughly identical prefactors. Because they're in the same conditions, right? They might be slightly different, but we're just going to assume that, again, we have a mixture of A and B that's all at 300 Kelvin. It's at some concentration. Everything is basically the same, right? They're not really any appreciably different. So what we can do is we can cancel this out. And doing some simplifications, we have that the product ratio is going to be equal to, again, I've got a bunch of exponentials, so I can put them all together. And I'm just going to kind of do this, and then we'll simplify one more step. We have delta G B plus delta GA minus delta GAB over RT. Okay, so the product ratio has to do with an energy difference right? Where we have a sum of these barrier heights and we subtract off the energy difference between A and B. All right, well, let's think about that really quickly. And right, because these are all referenced to the same thing, right? Delta GA is referenced to the energy of A, delta GB is referenced to the energy B, and then we have some difference between the reference energies for A and B. Right, so that means that GA and GB are interrelated. The difference between these has something to do with the difference between these two energies. Right, if we sum these all up together, you can see that they all kind of correlate to each other, right? As A and B move, that will change GB relative to GA. And if I move GA relative to GB, it's going to change things as well. So what you end up getting, that when you put all of these together, you get e to the minus delta G activation over RT. This number right here, this delta G, which is a terrible way to write things, but unfortunately it's the way we write it. This is the difference between the activation energies. Okay, so the only thing, so what that means is that the product ratio in this situation has nothing to do with the initial ratio of your starting materials, but rather it has to do with the relative rates of your two reactions. Okay, so what this is saying then is that if A and B can rapidly equilibrate, then KEQ between A and B does not affect the product ratio. The only thing that affects it, right? What this means, therefore, is the product that forms fastest is preferred. Let's look at an example of this. Of course, the problem set 6 is a really Nobel Prize winning example of the Curtin-Hammett principle. Let's actually maybe, well, let's work up an example real quickly. Let's look at an example. And then maybe I'll bring up the problem set. We'll talk about the problem set from that perspective. All right, so here are some examples. And I'm unfortunately I'm stealing these from Wikipedia, but they're actually quite instructive. All right, so I want to show you two kind of consequences of this. All right, so let's first look at this reaction. We're going to look at this methylpiperidine. This is, let's see, this is N-methyl 1, 2, this would be the 1 position, 2 position, 3, N-methyl 4-T-butyl piperidine. And this has, again, remember, nitrogen has a lone pair, right? And so in this isomer where the CH3 group is axial, and lone pair points equatorial. Kind of clean it out like this, right? And this is in rapid equilibrium, right? It's cyclohexane. We know that they equilibrate between the chair and the other form. There's an equivalent form. Where instead the lone pair points axial instead. And the methyl group points equatorial. Sorry, I didn't finish my plot there. Okay, and let me copy this name over because it's in my way. Right, and this can under conditions with methyl peroxide, or sorry, not methyl peroxide, with hydrogen peroxide, excuse me. You can oxidize this system to form a nitroso, NO. So this is with H2O2. Not the best cyclohexane ring in the world, I apologize. And what happens is basically the O oxidizes this lone pair, so we get an N plus O minus Zwitter ion. The CH group axial like this. Right. And we can also do the same thing to this, where we form the nitroso in the axial way, pointing up above the ring, and the methyl group is equatorial. Okay. So this reaction right, so we have an equilibrium between two different starting materials, right, that form two different products. Okay, they're isomers of each other, but they're different products. They have different energies. And when you go look at the thermodynamics for this process, you find that the energy difference between here, roughly, is about, I'm trying to remember exactly what it is. It's about let's see, A12 methyl strain, I think, is about 2 kilojoules per mole. Correct. A13 strain is typically diaxial strain. Yeah, it's about, let's say it's roughly 3 kilojoules per mole. And the one on the right is more stable. Okay, so let's think about what the equilibrium between these two are. What's the equilibrium constant? All right, so if we're at 300 Kelvin, right, so what's KEQ here? All right, well, that's E to the minus 3 kilojoules per mole. Well, minus 3. Oh, sorry, 3, positive 3, over RT, which is 0.00831514 times 298.15. Let me go ahead and calculate that for you really quickly. Minus 3 divided by 0.008314 times 298.15. So the equilibrium constant is about 0.3. Right? So that means that roughly, right, that roughly means that they're about 3 to 7, right? So this is about 35% of this. Oh, sorry, no, that's the wrong way. This is about 30, so it's 0.3, it's 3 out of 7 to 3 ratio. Yeah, we'll say that's roughly 35, 45%, give or take. Okay, so you have a material that by itself has an roughly an equal equilibrium, right? They're not really that much different at 300 Kelvin, right? You have a small preference for one over the other, but they both exist in large amounts. Okay, and then when you go do this experiment, again, you make a mixture of products. Right, and then if you go look at the product ratio, And again, these can also equilibrate themselves. Right? There's also an equilibrium here. But ideally, you would say, okay, right, this reaction is pretty much the same as this reaction, right? The only difference is that this H2O2 comes from above the plane of the ring on the right side, and here it kind of comes from the outside in the equatorial position, okay? So these are similar reactions, but there's a slight difference in the orientation of the transition state, if you will, where the O2 comes, the peroxide comes in and oxidizes the nitrogen. So, but in general, you'd say they're pretty similar. So let's go look at what the product ratio is. And what you find is that you make 5% of this and 95% of this. Okay. So not surprisingly, we would expect, and by the way, the ratio of these energy differences is about the same. So I'm just going to say here, delta G is about the same as well. Sorry, I don't want delta G here. Sorry, there's no point here. This is a real thing. Right? It's a roughly, it hasn't changed really. Because it's this methyl group that really contributes here. Right, so you have a product, a reaction that has basically 50-50, and then forms a set of products that are roughly equal to each other in equilibration if they can equilibrate, but somehow I make 5 and 95%. Right? And the reason why that is because of the Curtin-Hammett principle. The point of the matter is that this process here of the O coming in and attacking through the equatorial pathway, this is fast. So the rate is, so this is fast and not very energy, right? This has a small delta G factorial. And the reason why is because this O2 comes in from the side of the molecule. Right? It's coming in through kind of an unhindered part of the space. And so it can attack that that lone pair basically freely. But in this case, right, in the case of the one where the lone pair is pointing axial, right, this oxygen, let me push my electrons a little more effectively. Right, and you form water here, O plus water. Right, this oxygen needs to come in and it's going to be above the ring, right? And that gives you this strain, right? Because there are these axial protons, we'll draw them in a different color, that interfere, right? That interfere sterically with this attack. Whereas there is no steric interference here. So no sterics here in the transition state, and you have steric effects here. Oh, I have this flipped. Sorry, I have this flipped. Sorry, guys. This is slow. This has a large delta G. I apologize. I apologize. And so what happens is the energetics mean nothing here, right? Basically, these products are coexisting, but the fact of the matter is that one forms a product faster than the other one. And because the product ratio only depends because of Curtin-Hammett, remember the product ratio only depends on delta G, on delta G activation, right? Which is the activation energy of, say, A, we'll call this one B, right? A minus GB. And so this has a much faster rate. Sorry, this has a much faster rate. And this has a much slower rate of attack. And therefore, you get a huge difference in your materials, right? So you get an amplification, if you will, right? This is enriched. right? And the idea is that, right, and this is enriched beyond the expectation of KEQ between the products, right? The products are basically the same energy. Right? The products are the same energy, but we get a lot more of one than the other. Right? And that's because rate the KB, the rate for B, is much, much faster than KA. And so what this is called is what's called kinetic control or trapping, which is where you can trap and enrich a material way beyond your expectations from equilibrium, because you've arrived at those products with a rate of some pathway whose rate in competition is much, much faster than the other pathways. Right? So the idea is that these two pathways don't really make much of a difference in terms of their initial points and their finishing points, but the way in which H2O2 comes in and attacks the nitrogen is very different in both of these, and corresponds to one having a very fast rate and one having a very slow rate. And therefore, your product ratios reflect the difficulty of forming this one kinetically. Right? So this was what we call kinetic control. It says that the products, the result of your reaction, depends on the relative kinetics of them, not the relative thermodynamics. Right? So we're using rates to enrich things by making something faster than another thing. That's kind of a weird situation. Let me give you something that's a little more, maybe a little more easier to deduce from the Curtin-Hammett principle. I think this one's really quite cool. Now, let's see if I can draw this. This is a fun one. So this is the another example. It's the alkylation of this molecule called tropane. Right? And so let me draw tropane for you. It's a really quite cool molecule. So let me redraw this. I'm almost there. So there's this 6-member ring, and then between two adjacent rings, there's a little post that points up where they're connected, and there's a nitrogen here. Like that. It's got a double. So we're going to have, let me draw this. It's going to have a lone pair here, and we're going to methylate it on the other side. Okay. Actually, 1, 2, 3, 4, 5, yeah, 6. That's right. And this is an equilibrium with a different isomer where the nitrogen has rotated. So let me show you what the difference between these two are. It's kind of hard to see from this structure. But the idea is that there are two hydrogens kind of pointing down here. There's a hydrogen pointing up here. And on this side, there are two hydrogens pointing up. Right? So there are two H pointing up towards the nitrogen on this side. And here there's only one. Okay, because this carbon right here that I've highlighted here is kind of tilt downwards. This is kind of bent downwards. This is bent away. Okay. So this has a lone pair that interacts with two hydrogens here, and this has a lone pair that only interacts with one. So this equilibrium is pushed towards this because there's less steric interactions. This methyl group actually is pointing up in the air, so it's not interacting with anything. It's this nitrogen lone pair, and it only sees one hydrogen here versus two. And so the one on the right is more stable. So this is, so I'll just write it like that, right? This means it's preferred. So this is more stable. And this is unstable, less stable. I shouldn't say unstable, but less stable. Okay, well, I can react these with methyl iodide to remove that lone pair, to attack that lone pair with methyl iodide. So we use CH3I. Right, and methyl iodide again kind of looks like CH3 plus and I minus, assuming you're in polar solvent, but its idea is that it's a positively charged methyl group, and that methyl group attacks the lone pair. And so what you end up getting as your products let me erase this. I'm trying to get it right. There we go. That's nice. We put the nitrogen here, and now you have a dimethylated nitrogen. Like so. So you get these two products. Now, here's the problem. I've taken two unidentical molecules, right? Here you have the CH3 pointing this way and CH3 pointing this way, and I've replaced that lone pair with another methyl group. So these are the same structure, right? Right. So we can't really tell them apart, right? So there's a clever way to do this, right? So what we're going to do instead, these are basically the same. Now, let me just write that here, right? So again, these equilibrate rapidly because they're the same structure, right? Delta G is equal to 0 and KQ equals to 1. Right? Okay, so we're ending up with two products that are exactly the same energy, right? So we're starting with a starting material that's in competition with another form that's not stable, less stable, and we're forming an identical product. So now the question is, can we distinguish between these two pathways? Because you end up with the same product, how do you distinguish between them? Right? So there's a nice trick, and this trick is a very clever one. What they do is they isotopically substitute. So I put a carbon-13 here instead. So the carbon-12, I just add a neutron. Right? I make that carbon-13 instead. Right? Now I can make carbon-13 here or carbon-13 here. Right, so now I've made, again, two products. These have the same energy. Right? Oh, we just changed an isotope, but we haven't really explained why that wouldn't change the energy, but it doesn't. These are equivalent. So the KEQ is still 1 here, but I have two different products. One where the CH3 is over here and one where the CH3 is over here. Now we can ask a question. So which one forms faster? Right? Which one's the major product, rather? Let's put that question. Remember, it's always about the product ratio. So which one forms in more abundance? Okay, well, we would say, okay, well, we're starting with a material that equilibrates over here, prefers to be here. Both of these pathways end up with the same result. Right? So we don't have to think about the energy difference of the products at all. Result is exactly the same, but now we have two pathways for our methyl iodide to come in. It can come in this way or it can come in this way. And that will lead to, with the carbon-13 being placed at different places, right? And so if we have a way chemically to discriminate between these two situations, basically we have some chemical tracer that allows us to say the carbon-13 is on this side, or the carbon-13 is on this side. You can do that with NMR. We can figure out which one forms faster. All right, well, let's see. Let's just do a very simple approximation, right? Say we have more of this starting material. Okay, these really aren't that much different. We have more of this. They both form the same thing. So maybe this would be what we form the most of, right? The product that comes from the most stable starting material. Right, so by using thermodynamics, we would assume that this is the minor and this is the major product. Right, because this is the major starting material and this is the minor starting material, and you're going through the same reaction to the same end product, right? So it shouldn't make that much of a difference. So thermodynamics would predict that this is major and minor. What you find in experiment is the opposite. This is the major and this is the minor. Okay, because what actually happens is that the transition states of these two pathways are different. Right? Remember that when we're in competition, if you have competition between two things that are equilibrating in a competitive equilibrium, the fastest forming product wins out. So if we think about what the transition state looks like for this process, so again, let's just copy it over so I don't have to keep drawing it. Right, if we think about the transition state, remember we have these two hydrogens here and one hydrogen here. The fact of the matter is that this hydrogen in particular that's nearby is very close to this lone pair. Now there's only one hydrogen close to that lone pair, but there's still a hydrogen here. And when this methyl iodide comes in, right, it's going to, the way it attacks is through SN2. Right, like this, right? And that hydrogen impedes, right? This hydrogen sterically impedes the approach of the nucleophile or the electrophile. Electrophilic CH3 plus is sterically hindered by axial hydrogen. Right, so even though this is the stable precursor, this is the slowest reaction, or the most energetically unstable transition state, whichever way you want to think about it. Meanwhile, if we look at the other material, again, we have that lone pair sitting here, right? And we have these hydrogens that are kind of pointed out in this direction, like that. Here, that there is no direct, that hydrogen that was interfering before on the opposite side of the ring is now not really pointed in the same direction anymore. These hydrogens are kind of canted. These hydrogens are kind of pointing away, and this methyl group is free to come in. This electrophile is free to come in from this direction, and it's not impeded, right? Not sterically impeded. No steric hindrance. right? And so this is the fastest reaction. With the unstable precursor. And because these two precursors are constantly in equilibrium with each other, they're constantly rapidly equilibrating, the one that is most likely to react, regardless of the energetics, is going to be the one that forms the products most rapidly. And so if the more stable molecule is really, really slow, these are constantly being reacted, the less stable ones, to form the major product. And we're just going to slowly and slowly build up more and more of these over time because they're more likely to form. And as I start to run out of the less stable material, the equilibrium will bring more material back to me, right? As I lose the less stable precursor, Le Chatillier's principle says the stable one is going to isomerize over to maintain that ratio of starting materials, right? The equilibrium. So I constantly have a free source, if you will, of the less stable isomer that reacts very, very quickly. And not surprisingly, that's the product that I see in my reaction. Okay, so this only happens when you have this kind of competition. So if you're allowed to equilibrate your starting materials between two different pathways, the one that wins out is always the fastest. Doesn't have anything to do with the thermodynamics necessarily. It has to do with the kinetics. So sometimes you can trap less stable materials and make kind of weird structures that you wouldn't expect thermodynamically because you've set the kinetics up in the right way so that they form faster. Okay. So the last thing I want to mention, maybe we'll finish a little early today. Is that in this situation, so let me bring back my reaction scheme. This is my reaction scheme. So some observations, if you will, some observations of this. Right. What if, for instance, we have a situation where the rates of formation of the products are much faster than the equilibration? Okay, so what would that look like? Right, what would the reaction coordinate for that look like? Again, that would be where you would have P1 here. It would have a little barrier to A, and then A has a massive barrier to B, which also has some reaction to P2. Okay, so what this means is that A and B do not rapidly equilibrate, right? And this means, of course, that it's not steady state, right? So that means that if A cannot be replenished by B, and etc. Right? Okay, so this is a different situation, right? Here we don't have competition. I mean, we do have competition between A and B, but it takes a really long time for A to become B, right? So imagine that A reacts very quickly and form P1, right? So I'm constantly losing A's, and I'm just losing A's, right? The A's are just going away, and B's are never coming over this barrier, right? So the rate of isomerization from B to A is very slow. So the concentration of A and B are constantly changing and depleting as the reaction goes to completion, right? Here, Curtin-Hammett doesn't apply because the amount of P1 that I get only depends on the amount of A I have and its rate. And B only depends, the P2 only depends on how much B I have, right? So in this situation, this means then is that dP1 or dP2 over, oh, sorry, P2 over P1 is only going to be dependent on how much A or how much B I have, right? And so it's actually going to be proportional to the equilibrium between A and B. So the relative energy of A and B. Sorry, no, that's not true. Sorry. It's only proportional rather to the delta G of the products. Sorry, that's the right one. Right, so if you have two reactions, A to P1 and B to P2, the one that you're going to form the first of is the one that is most exothermic and the most kinetically favorable, right? So thermodynamics takes over here, right? So what this means is that the major product is the thermodynamic one. Stable one. And not the fastest forming. Okay, so that means again, if P2 is if P2 is more stable than P1, then the ratio of P2 over P1 is greater than 1. So it basically just depends on the stability. So that's what you would expect, right? For instance, this is kind of like you're always going to form the most stable products, right? So basically what this says is that A is given as much time as it wants to react to form P1, and B is given enough time to react to form P2. Naturally, the thing that forms the most is going to be whichever is the most stable. So this is just a standard result, right? Basically, what I've done is I've taken my competing reactions and split it into two. Right? I basically just cut this reaction in half so that it's basically two steps, two processes that are occurring separately. Right? And so the one that forms the most is going to be the one that's most stable. So the idea is, again, A to P1 is separate from B to P2. So thermodynamics, which is the delta G of products, determines the abundances. Product ratio. All right, we have a term for that. Right, remember that we talked about the concept of increasing the amount of material you have through a reaction that's faster than the other one, even though it might not be more stable. We call that kinetic control because it is controlled by the kinetics of the process. This is controlled by the thermodynamics. So this is what's called mouse is freaking out, thermodynamic control. All right, so the difference between these, and I'll just kind of say this in general. So in general, reactions are kind of in between. They're not one, they might be competitive, they might not be competitive. The barriers, it depends with the relative heights, but there are general limits, right? So in general, you could say that Ka, Kb are often competitive with K1 and K-1. Right, so they might not be, one might not be 10 times the size of the other one. And in fact, in the problem set, in the example that I give you in the problem set, the ratio is 4 to 1. They're only 4 times different from each other. Right, so the barriers are fairly similar in these situations. Right, kinetic control, which is that products formed based on which forms faster is promoted at low temperatures. In general, if you have a system that's in competition like this, where you have these things constantly competing with each other, typically when you bring the temperature down of your reaction mixture, the kinetic limit, the kinetic control, which is that the product that forms the fastest, tends to dominate. So low temperature. And then thermodynamic control, which is where products form based on their stability, on their energetic stability. Right? The equilibrium between them has nothing to do with the rates. This tends to be dominant at high temperature. So you'll find that in the problem set. In the last couple of questions, I asked you that question about it's a slightly different way, but what you'll find is that in the problem set 6, that as you tweak, if you have, in this situation, you're using a catalyst. The catalyst determines the heights of these barriers, and the height of the A barrier is slightly different than the B barrier, like that difference of activation energies that the Curtin-Hammett principle requires. What you find is that the product ratio, given a fixed difference in barriers, right, Ka and Kb are fixed, and you change the temperature of your solution, the amount of the kinetic product that you get increases as temperature goes down. So you start forming the kinetically fast product, even though it might not be the stable one, more rapidly, and that product tends to be enriched at low temperature. Now that seems odd. You would think I would need to have higher temperature to be able to situate myself in an unstable structure, but that's not how this works. Here, the kinetics dominate. So at low temperature, and especially in the homework, and you'll see this, the math works out exactly this way in the homework, that low temperature puts the reaction into a condition where the preferred product is the one that forms fastest, but not necessarily more stable. Meanwhile, as you crank the temperature up, the opposite happens. So you crank the temperature up, assuming fixed rates, the product that the slower forming product, which may be the more stable one thermodynamically, starts to appear more and more and more, right? What you actually find in the problem set is that it's much easier to get enrichment of your products of one isomer over another at low temperature than it is at high temperature. And so that was one of the kind of consequences of the research that was done that I summarized in that problem set. Right, so we talked about these kinetic and thermodynamic controls, and these are really, really, really important concepts in chemistry in general, because this is how we make stuff. Because sometimes the thermodynamic product is not what we want. Right? Sometimes, for instance, biology will make the thermodynamic product that we want of some material, but we don't want, for medical reasons or what industrial reasons, we might want the other form of that product that industry doesn't, that the world doesn't make. And so we might have to come up with a different process that allows us to use kinetic control to create that higher energy material, the less stable material, instead of the more stable. All right, so these kinds of concepts are used everywhere in chemistry. And one of the reasons why we do things at low temperature in particular, one of them is that maybe you don't want your reaction that's exothermic to get too hot. That's one reason we run things cold. So if they're very exothermic, you want to run them cold. But also because we might want to trap high energy products and enrich them instead of the thermodynamic ones, which we might not want. Okay, so you'll see examples of this all the time in the literature, where people will cool things down, not because of exothermicity or anything, but because of the kinetic control, right? They want to trap the fastest forming product, not the thermodynamically stable one. And people have used this to do all sorts of crazy stuff. Now, for instance, one of the examples that I really like is that you can, with the right choice of catalyst, if you take a tertiary halide, something like t-butyl chloride, right? You've got this big bulky methyl group, all these methyls on it. We know that doesn't go through SN2, it only goes through SN1. There's no back attack on the butyl groups. But you can set up with the right catalyst and the right substrates, you can actually set up the reaction so that the SN2 reaction is faster than the SN1, and then you drop the temperature and you form SN2 products with your t-butyl. You can force reactions into unfortunate situations and trap high energy conformers or things like that by using these competitions and then cooling things down to drive the thermodynamic products away and to promote the ones that form quickly. People do this all the time. Basically, this is one of the most easy ways to break the rules in chemistry by using kinetics to your advantage. Okay, any questions about that? Okay, so that's all I have for you today. I have two very short topics for Thursday. We're going to talk about another technique in kinetics called the isotope effect. This is a technique that chemists use all the time to determine mechanisms. We'll use isotopes, deuterium, carbon-13, things like that, to learn about changes in kinetics, and that tells you something about the reaction. It's a really, really common technique of physical chemists that organic chemists and other types of chemists use, the kinetic isotope effect. And then I might talk just very briefly at the end of class about microscopic collisions between molecules and talk about kind of the microscopic part of reactions, if we have time. All right, that's all I got for you guys. Have a good one. Thank you, Chris. Yeah.
I see.
This is-
Yeah.